one of your classmates came up to me and said, hey, I happen to notice that I forgot I put it on there. Okay, some of you have never had me before. You're starting to go, oh my God, what is this guy? But anyway, I forgot to put it on there that you could get 20 points extra credit if you just read a book, all right? And kind of do like a 3 to 4 page, double-spaced. Don't go to like Pica 20 or something like that, bold, type thing. But, 3 to 4 pages of, what the book was about, how it impressed you, all that kind of stuff. What kind of books was the question. And it basically science books for the general reader. Here's some examples. Now remember, I was a math teacher before I became a physics teacher. So we got all these things like the University in a Teacup. She's a very good writer, Casey Cole. And then here's like God's. You don't have to read these, but if you've got anything by Feynman, by Richard Feynman, there's a famous book that he put out called 6 Easy Pieces, which is basically if you're interested in chemistry and physics. He was a Nobel laureate in physics, but he could actually explain this stuff. And this is one of my favorite books. This is by Natalie Angier. She's a science writer for the New York Times, and she's not a scientist. She's a journalist, and she writes very, very well. And basically, this book, The Canon, is about the 8 big questions of science. In other words, she found a biologist, a chemist, a mathematician, a physicist, and said, okay, if you could only tell people one big thing about your field, the most important thing for them to know, what would it be? And that's what this is. And it's engaging and everything else. Stephen Hawking, some of his writings is like, whatever, but you can do that one or almost anything. And this is a very good biography. I mean, it's long. It's biography on Uncle Albert, okay, by Walter Isaacson, who wrote I think he won the Pulitzer Prize for his biography he wrote on Franklin, Benjamin Franklin, just a few years ago. Okay, so that gives you the flavor of if you want to go buy a general science for the general reader. You don't have to read like quantum mechanics by by Schrodinger or anything like that. That's beyond the pale. So don't need to do that. All right, now here's the way class is going to run so that we can get. We've got our AV crew here, and I made sure that I got a coffee stain on my shirt because this is going to be broadcast of millions. Because I know everybody is waiting just can't wait for the next installment of Physics 220 to hit the YouTube site. Where it's going to go is we're going to go through the slideshow to the end of Chapter 18. So we'll have covered all of Chapter 18. I did do you dirty again. There's a new assignment on Wiley Plus waiting for you as we speak. All right, and it's not due till Monday. It's due Monday at noon, and this just covers up through Chapter 18. Okay, and then once we get done with the slideshow, I'll turn up the lights again, and we will go into the. We will do the quiz, do a little quiz, which will be kind of fun. And then we will do the homework problems, make sure that we understand those homework problems, and do problems 10 and 14. And then I think we'll be done. Okay? You can turn in your quiz. Jared came in late, right? Or just got here? Did you get your quiz back? What's your name again?
David.
David Smith.
Yeah.
Yeah. Here we go. All right. Okay. Now I think everybody that's here. Okay. Now let's have fun with rods. All right. Now then, I was talking to Dr. Vrobel. This is some kind of material, some kind of plastic material, and we're going to rub it. It's not completely plastic because it's a good conductor, and we're going to see what happens here when I rub this thing vigorously, as they say to do. Okay, so you rub it vigorously. All right, and now let's just say it's positively charged. What the heck? Why not? All right? Say it's positively charged. So try this again. I'll probably pick the only one that doesn't work. What? I don't know. Oh, there we go. There we go. Ah, there. That's a little better. Put it over here. So if this is positive, what's the charge on this? Negative. And what would happen now? So let's do this. Let's rub this guy. Get him all charged up. So we said that he was what? Charged? Negative. He may be positive. We don't know. But since we set the standard that this guy was positive, now, if I rub him good, and if I'm going to put him next to him, what's going to happen? He should repel it, I hope. It attracted it. What the heck's going on? Oh, there we go. No. Put it here. Because they're the same. Well, then they should repel, right? Oh, I changed the charge? I don't know. I don't know what I'm doing up here. I've never done this experiment before. But let's see. Those two attract. Okay. Now, oh, you said put this one up here. And then rub this one. No. Well, what happens there? Please repel. It repelled. All right. They've got a good demo on the Wiley Plus site, believe it or not, of this whole thing, of this silliness. What's this one do? Let's just see. All right, so here we go. Ooh, that's big time. Ooh, that's a good one. I like that. All right, so now let's try this one. Glass. Can't do anything with glass. Clean your room. No, it's not doing anything. But this one, I thought no, it's attracting. Okay. Did it do that before? Did it attract before? Okay. Let's see what this one does. Real quick, then we'll move on. It might. That did nothing. Oh, well. Let's get rid of this one. Let's put this one back. Put this one back. There we go. Now, all right. Let's rub this. Let's say it's positive. Oops. Center of mass. I do know about that. There we go. Okay, so what's it going to do? Oh, it's attracting. Pretty good. Let's see what it's going to do to this one. It's attracting that one too. So these two should repel each other, right? Yeah, these two. Let's see. Because
I think when you rub it, then it's going to attract it.
If you would have done it
Oh.
before you rubbed it, it probably would have repelled it.
yeah, let's put the fur up there. See if it repels it. Good idea. Oh, because I'm removing charge every time I'm doing that. Thanks. Thanks, James. Okay, good. Yeah, just throw my stuff out on Front Street. All right, but anyway, well, that was fun. That was fun as an all-night dentist. But anyway, okay. Let's move this to the side. Actually, it is kind of fun to do once you figure it out. I needed to practice more. Remember, rehearse. Okay, now what I was supposed to do, I think, can I turn this off? Do not turn this thing off. Okay, I'm being waved off. Wave off. You're too low, too low. Okay, here we go. We're going to turn off the lights, and let's start the laser light show for today. Oh, I was supposed to grab the gyro mouse, and I'm supposed to stand over here. This is the way it's supposed to work. All right. And they promised me that this would work. What did I do? Oh, Coulomb's law. Can I go back?
You can, it actually mouses on a table,
Oh,
or should.
should mouse on a table? There we go. Oh boy, this is going to drive you absolutely crazy. All right, good. There we go. All right, now, so we've seen this. Now, this is like a plastic thing, and you got the ebonite rod coming in there that's negative charge, and so it polarizes it. But now, let's get down to brass tacks. There is a force out there, a very strong force, incredibly strong force. It's the electrostatic force of Coulomb's law that we're going to look at now. I don't want to do that each time. Okay. All right, now, here's Coulomb's law. If I have this charge here, I'm not supposed to get close to the screen. All right, this charge here of Q1 and this negative charge of Q2, notice they're attracting each other. Just like we found in our experiment over here, right? Okay? And then if they're both positive, then they're going to repel each other, and there's a force there. Anybody remember what the force of gravity was? Gravitational, the equation for the force of two bodies? Big G, there we go, we're getting close.
And 1 and 2 divided by
Divided by r squared, but divided by the centers of them, the distance part of the centers of them squared, okay? So we had F equals big G, M1, M2 divided by r squared. Let's take a look and see what Coulomb's law is going to look like.
You can probably just click it.
Okay. You think?
Just pick it up and click it.
Just pick it up and click it. All right. Okay. All right, Coulomb's law, the magnitude of electrostatic force. Here we go. The magnitude of electrostatic force exerted by one point charge on another is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. What does all that mean? It means this. It means this. There we go. F equals K times Q1 times Q2. There's our two forces. There we go. Now oh, come on in. You're fine. You're fine. It's just that now millions of viewers can see you. Okay. All right. And here's a new constant. Remember we had the big G, which was 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. This is a new guy in town. He's E naught, and I'll put him up there. You got one more guy coming to join him. There he is. Okay, you got K, which is equal to 8.99 times 10 to the 9th newtons. So in this course, get used to using your scientific notation key. You use it a lot. Okay? In fact, one of you has already come to my office, and we saw that the only problem we were having was we forgot that microcoulombs meant to take it to 10 to the negative 6 when you're actually ready to calculate. Okay? All right. So we've got this K. This is actually, this little echo naught is what is known as the permittivity of free space for an electric charge. It's a constant. Okay? All right. So when we flip that over, and it's due to a lot of calculations and good old Maxwell, we can thank him for this one. Basically, there's the constant. So you take Q1 times Q2 divided by r squared. Now, you all know with beta Brett, in fact, you're going, I wish he would hurry up because I just can't wait to get to lab, right? Okay? And you've read, I know you read your lab, and you're all excited about going down there. Now, they do this Coulomb's thing a little bit different. Okay? They do it in a calculus vector way, and don't panic. We do it with absolute values because we're just going to stay in good old either one-dimensional thing here along a line or two-dimensional, where we got to go to cosine and sine and stuff. All right, but that's key. F, the force between them, is K equals Q1 times Q2 divided by r squared, and then we figure out by the orientation and by the charge which way that arrow is going. All right? Okay? the way that your lab manual was explaining it, by the way the vector calculus is set up, it will tell you which direction the force is going. We look at the picture and we decide, okay, because we're going to use algebra. Okay. Oh, wow. That worked pretty good. All right, Coulomb's law. All right, now, oh, here we got a proton. Okay, example, model of the hydrogen atom. Here's Bohr's model of the hydrogen atom. You got a proton in the middle, okay, and an electron zooming around the outside. Which one's heavier? By what factor? We'd say it's almost by a factor of 4, because he's 10 to the negative 27 kilograms, and he's 10 to the negative 31. So a factor of 1 is 10 times 2 is 100, 3 is 1,000. So it's about 10,000 times more massive than that little electron flying around. But what about their charge? They're equal. Yes, their charges are equal. Okay, so here we've got a model of the hydrogen atom. Okay, in the Bohr model, the hydrogen atom, the electron's in orbit. Okay, determine the speed. Oh, this will be fun. Determine the speed of the electron, assuming the orbit is circular. Uh-oh, Rut-row-Rorge. We've got to go back to chapter 1, or to the first semester. Some of you are going, I didn't have you first semester. Don't worry. We'll take it from there. We know that. All right, so now, this has a force on it, just like when we did the gravitational force. Remember when we had like Neptune circling about the sun or something like that, or Mars, and we did that gravitational force. We figured out as G equals m1, m2 over r squared equals mv squared over r. So write that formula down right now. For things in orbit, remember the force is equal to the mass of the object in orbit times v squared divided by r. Do you all remember that from chapter 5, first semester? Okay. So, guess what? Those two forces are equal to each other. So that, I bet $1 to a donut, so they're taking this force. Let's see what they do. Okay, they put the picture up there, and they go, all right, here's the force between the, oops, I already violated, but that's all right. Here's the force between the proton and the electron. You got K, here's our K, times, now they just went ahead and went Q squared. If I'd have written this out, I'd have probably put, now notice what they're doing, they just went ahead, since they have the same charge, and then the distance between them was this. Here's the radius between them, and they square that. And so we wind up with this force of 8.22 times 10 to the negative 8 newtons. 10.22 times 10 to the negative 8 newtons. All right, that's the electrostatic force between them. All right, now we've got to figure out how fast it's going. I think we can do that. Ah, here we go. F equals mv squared over r. I'm sorry, I didn't know they would come up and give us that. They did. Okay, so then, of course, they do what we were supposed to do is set this mv squared over r equals this guy. They make it all look very difficult and everything else, but all you got to do then to solve this thing is multiply by r, multiply r times the F, divide by the m, the mass of the electron, 9.11 times 10 to the negative 31 kilograms, take the square root of the whole thing, and that thing's flying around there. 2.18 times 10 to the 6 meters per second. Okay? Oh, I'm supposed to walk in front. Forgot about that. Okay, so Coulomb's law example. 3 charges on the line. Okay. Oh, did you all bring calculators? All right, break out your calculators. Let's just do the quiz right now. You'll be all right. You'll be all right. We're going to do this problem. And hopefully we'll get it right because we're going to go on to the next. So go ahead and take a minute. What we want to do is determine the magnitude and direction of the net force on Q1. Okay, we're going to determine the magnitude, and they helped us out a little bit already by giving us the free body diagram. Okay? Now then, forces are scalars or vectors. Which are they? Vectors. They've got, what's a vector do for us again? Right, magnitude and direction. Okay, and then if they're the same units in newtons, we can just add them together, especially if they're just going in the same line. All right, so go ahead and see if you can figure this guy out. Some of you who brought, I just realized, some of you might have copied off the notes. You got the answer right there. Oh, well. But all of you will get the answer eventually, but just try it. Let's try it now. Give yourself, see if you can negotiate that calculator. If you forgot your calculator, maybe someone next to you has one. So take about 2 or 3 minutes to figure that out. All right. This will just be problem 1 of the quiz. There's another one. I've got another one lurking. We have it? Almost. No, everyone's still working away. This might have been helpful to do problems 10 and 14 from your homework. If we'd got this far Monday. Oh well. Live and learn. All right. Okay, it looks like most of you are done. Relax, because we're going to go to the right answer on the next page here. First of all, let's say I've got Q2 and Q3 and I've like pasted, I'm holding them on there. I've like taken a small spindle of some kind of and hammered it through these little bitty charges. But Q1 is free to move, all right? Which way is he going to go? Which way will he go? To the right or to the left? To the right, right? Because he's going, hey, there's -7 of the opposite over here, and there's only -4 of the opposite over here, so I'm going to go flying off to the right. Exactly. All right, let's see what the actual numbers, let's run the numbers, as they say. All right, here we go. So the force between 1 and 2 is the absolute value of that force, the magnitude of that force. And that's the other thing. When you're, for some of you that are kind of new to the whole Cutnell and Johnson way of speaking, whenever they talk about magnitude when you're doing a homework problem, they just want the absolute value. They just want the number. They don't really care about a direction, a positive or negative sign yet. So the magnitude of F12 is 2.7. The magnitude of F13, by doing that very long calculation, if you didn't have a calculator today, this would be impossible to do almost. So we did it old school, we used to do it, but anyway. 8.4, and so since F12 is going to the left, it's negative. Add them together, you get 5.7 newtons. Should be your final answer. Okay? Oh, now everybody's favorite. The next thing we're going to look at is what would happen. All right, so the quiz. So problem 1 for the quiz is over. We'll go to problem 2 here in a minute, a little bit later on. Let's take a look at this. The other thing, too, is we can do it in 2 dimensions, too. All right? We can do it in 2 dimensions also. So we wind up with a net. Notice we've got F12 is we're going to have to break it, since it's cattywampus, we're going to have to do what? Break it down into its components. Okay? And so it's no different than what you did before with your force vectors, starting all the way back to chapter 4 last semester, when you'd have a vector that wasn't strictly on the y-axis or strictly on the x-axis. You just, to get it along the x-axis, you take it times the cosine of the angle, and go along the y-axis. You take it. So let's kind of walk through this one, because right here, for Q1 to Q, for this force right here, F1 to F3, your Q1 and Q2 will be the +4 and the -5. But again, we're just going to look at the magnitudes of them and know that he's going to want to go to the right. Okay? And then for the F1, F2, you have to use the cosine to find he's going this way, and he's also going up. You'd have to use the Q1 and Q2 of that one. All right? And I think they do that in the next slide for us.
Where are you getting when you charge the -6 and the -3? Why does that show?
Where?
Is this the same as the last one?
No. Oh, no. New problem. Yeah, this is a brand new problem. Q1, Q2, there are 3 different charges. And now we're trying to find the pull on charge 1. Okay, now. All right, now, here is an important concept. Okay? Charges out there emit an electric field, just like the sun has a huge gravitational field that's keeping the Earth going around it. Okay? All charges exert a magnetic field, an electric field. All right? Okay? And we measure that electric field we take what is known as a test charge. We take a small little charge like Q naught, and we're going to say that it's a positive charge. All right? So if it's a positive charge, it's going to be attracted to this negatively charged sphere. It's going to be attracted to that negatively charged ebonite rod. Okay? And we can measure that force. We divide that force by the Q naught, okay, by the charge, and guess what we've just measured? The electric field there. Okay? So we've got machines that will tell us what the force is here for this little bitty charge that we put there. We divide out that charge, the test charge, and boom, we've got an electric field. All right. Okay, example, a test charge. The positive test charge has a magnitude of 3.0 times 10 to the negative 8 coulombs and experiences a force of 6.0 times 10 to the negative 8 newtons. Aha! What we want to do is, okay, so we know the force, we know the test charge. How would we find the electric field? Dun, dun, dun. Yes. Find the force per coulomb that the test charge has. In other words, experiences. And this is the last time I'll do the fly-in thing. I apologize for that. All right, predict the force that a charge of 12 to the 8th coulombs will have, would experience if it replaced the test charge. Okay, there's the picture. All right. Okay, so the force, and then part B was this one. All right. I screwed that up. All right, so we want to first find the force per coulomb, and this is what Melissa gave us. She said, oh, just take that force that they told us and divide it by the coulombs of the test charge, and we get 2.0 times 2.0 newtons per coulomb. Get that in your brain housing group. That's the way you measure an electric field. Okay? Is newtons per coulomb. By the end of chapter 19, we'll also know you can measure it volts per meter. Okay. But right now, it's newtons per coulomb. How many newtons per coulomb is that electric field? And so if the electric field there is 2.0 newtons per coulomb, and we put a new charge in there, a new charge of Q, here would be the new charge of Q right here, it would experience a new force. Okay? It would experience a new force. All right. Good. Electric field. Definition of electric field. Here it is. Don't forget this. It'll show up. E is equal to the force that's there divided by Q naught. Okay? The SI units for the electric field is newtons per coulomb. That's too quick. Oh my. Okay, good. All right, there we go. Okay. Notice. The electric field here, and you will become experts on this shortly, here in about 3 minutes. The electric field is pointing this way. And when I put a positive charge there, the positive charge wants to go in the direction of the electric field. Okay? A negative charge, guess what it's going to do? It's going to go in the opposite direction. And why is that? If I have this, if I put with this positive charge, which direction does he want to go? What's he going to be attracted to? The ebonite rod and this sphere, or this sphere with the positive charge? Which one attracts him? If he's positive, which way is he going to go? Yeah, he's going to be attracted to these two guys. So that's why he wants to take off that way. Okay? And this one, since the electric field is going that way, he's going to go this way. Okay? He's going to want to go that way. So a negative charge will go against the electric field. We'll want to go taken off against the electric field of force opposite the electric field. Okay. All right. Example 7. Electric field leads to a force. Well, we figured that out. Okay. Determine the force on the charges A and B. Okay, if we know that the electric field is 2.0 newtons per coulomb, we already did that once. We already found we estimated the force. So this leads to another thing. Okay. So the force is equal to the charge times the electric field. All right? And then again, we just have to figure out which direction it's going to go by the picture. All right, good. Okay. Electric fields are also vectors. We can add them up. They are also vectors. Okay. So we can add electric fields up just like we would vectors. Okay, so here's example 10. The electric field of a point charge, okay, now an isolated point charge has a charge of 15 microcoulombs. That's that Q over here. Okay, now we're going to put a test charge that's 0.2 meters away, and it also has a charge of 15 microcoulombs also, and determine the electric field at point P. Okay, so here's what we're going to do. Oh, so what's the first thing we got to do? We got to find the force. Okay, F equals Q1, K Q1, Q2 over R squared, just like the, it's analogous to the gravitational force between two bodies. And then divide it by the test charge Q. And this will lead us to the second equation that you have for the electric field, which is this. And this is about to drive me absolutely nuts. I'm going to turn it off here in 1 second. But first we've got to get to electric field lines. Okay. So for the one, we found the force is 2.7 newtons. Okay. And then if you divide that by the coulombs, you wind up with 3.4. That's the answer to A. The answer. And then this leads us to the next. This is it. The last equation, point charge Q, E equals K times Q over R squared. Okay? Now, if E is a vector, let's go back. Oh, dear. Nope. I'm moving it. All right. Well, let's just take a look at this picture. Okay? Now, notice. E2, remember. E2, he's pushing an electric field out that way. All right? E1 has an electric field coming off this way. I'm going to just tell you this right now before we get into the picture. Positive charges, the E field is leaving them. Positive charges, E field is radiating out from them. Okay? Negative charges, guess what they're doing? They're taking an electric field that's coming into them. All right? So, this guy, this charge here, here's his electric field. See, he's radiating out this way, like this. And what did we say the equation for that was? It was the electric field equals KQ divided by R squared, right? Okay, so if it's KQ divided by R squared, as it gets further away, that electric field gets weaker and weaker and weaker and weaker. All right. E2, he's pushing that way. So we could actually find a place, probably in the middle between two positive charges, where the electric field is 0. Okay? Because remember, now, think about this. We'll see a picture of it here in a minute. Q2 has a bunch of electric field lines. They're all uniform coming out off of him. Okay? They're radiating out. This guy, looks like a porcupine too, with electric field lines radiating out. So when we start to bring them together, the electric field lines start to bend apart from each other, and eventually there's going to be a spot between the two of them where it's going to be 0. Okay? Right? Because you can tell by this picture, if I add these two vectors, if this vector is the same magnitude as this vector, they're going to be equal what? 0. 0. All right. Oh, that was just a wild. We'll talk about parallel plate. Here we go. Here's what I wanted to get to. Okay. Sorry. Oh. All right, so here we've got time out. Tired of this. Okay, I can't teach that way. I'm just going to be honest with you. All right, so we're going to turn this off. Now we're going to go to this regular whiteboard, okay? I'll turn off the projector. It's driving me nuts. Can't do it. I try. It's got the nice pictures and all that stuff. So those viewing at home, I apologize. Let's go back. Let's recap what we learned the right way, the old-fashioned way. All right, here's the big idea from what you just learned. There's two charges. Let's say I've got two charges. One is plus 3.0 microcoulombs. This guy is negative 2.0 microcoulombs. All right. We'll call him charge A, charge B. Which way is the force? Here's what I want you to do. The force on A caused by B. Okay, the force on A caused by B. Which way is that going? To the right or to the left? Which way is the force on A caused by B is going this way, right? Here's FAB. Okay? And that would equal, this force would equal 8.99 times 10 to the 9th power, yada, 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 bunch of stuff. Well, I know what it is. It's newtons, meter squared per coulomb squared, times 3.0 times 10 to the negative 6 coulombs times negative, well, we'll just say 2.0 times 10 to the negative 6 coulombs divided by, oh, I forgot to tell you how far apart they were. Let's say 0.15 meters. 0.15 squared. There we go. And we know it's going to the right. We know it's going on the positive x-axis. Okay? It's going along the positive x-axis. What about the force of B, the force on B caused by A? The force on B caused by A. Which way is that one going? To the left. It's going that way. Here's the force of B caused by A. Beautiful. All right, now, force of B caused by A, that is here's a question. Is it going to be the same magnitude as the force of A caused on B? Yes, it is. It's going to be the same magnitude, just different direction. Okay? And it's going in the negative x direction. All right, now, let's start one little charge of 3.0 microcoulombs right here. Okay? And because it's 3.0, positive 3.0 microcoulombs, I'm going to just go ahead and draw 3 field lines coming off of it like this. That was terrible. I should have had them at 120 degrees to each other. So I'll do that. Do it this way. There we go. Pretend they're at 120 degrees to each other. Okay, so they're nice and uniform. All right, so they look like that. They got field lines that are coming out like that. Now, those are their electric field lines. And the electric field, let's just say I'm going to pick a point out here, and I'll just reorient it as say, okay, I'll just say that for right now, we're just going to pretend that this is the positive x-axis going down like this. No biggie. And we can do that. We can say, oh, what's the electric field at this point P? What is E at P? What is E at point P? Oh, well, first of all, I got to know how far away it is. I got to know how far away it is. I'd say, oh, let's make it 0.2 meters. And so the electric field there, E, would equal K times Q over R squared. So, is the electric field stronger at 0.1 meters? Would it be stronger? The electric field is stronger. So the force starts to get stronger too. And the force depends on how big that test charge is, or that other charge that you put there. Okay? The electric field will stay the same at this distance from this charge. It'll stay the same. Okay? That distance from the charge. But the closer we get in, the stronger it gets. The stronger that force gets. Okay? There. That's what I was trying to explain in that 35 minutes of slideshow stuff. All right? That's it. That's the big idea. And the other big idea is this. E is equal to F over Q naught, where Q naught is called what we call the test charge. Okay.
In that top equation, the K times Q divided by R squared, what charge do you put in there, the 3?
Exactly. Well, Ms. Braces came up with the key thing. This Q is this. This Q is a test charge that I don't have in this picture over here. Okay? But if I wanted to find out the electric field here, if I wanted to find out the electric field like right here, I would use this guy as a test charge and use him as my Q. Okay? In other words, I'd find the force. Okay, so what force do we feel right here? Okay, I could find the force by the Q1 times Q2 over this distance, R squared. No. Ooh. Erase all that. It's all wrong. It's all wrong. I can't quite do that because we'd have to. That's not quite that simple, but for the most part, this is the Q of the test charge. Okay. Not this Q. Find the electric field. All right, now let's do. Here we're moving on. Let's look at electric field lines. Then that's about all we'll get done today. I always forget how difficult Chapter 8. I always think, oh, this is easy. Well, yeah, it's easy because I already know it. But if you're just learning it for the first time, it can be kind of tricky. All right, so we're going to stop on electric field lines, but here's what we're going to do. Let's say this is positive 4 microcoulombs. And so let's just draw 4 electric field lines off of it. Now, since he's plus 4 microcoulombs, I can also do this. I can draw 8 electric field lines off of him. Can I draw 6? Wouldn't be a good idea. But I can draw 12. I can draw 16. I can draw 20. Y'all see what I'm saying? Just take a multiple of whatever this is. And that's how many field lines you'll you'll draw. Okay. So I've got 8 drawn there. And let's say I've got a negative 2Q microcoulombs over here. Okay? Well, how many of these electric field lines, of these 8 electric field lines, is that negative 2, do you think, going to suck in? Well, how many do you think? 4. He'll actually take in 4. Okay? Because I've got double the amount that I need for this guy, so I'll have double the amount he needs. Okay? So he'll look like this. Yep. 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 Okay? So if I put a negative 1 over here, these 2 guys will get him. Well, like that. Notice they don't cross. And I'll put a negative 1 over here. And he'll get 2. Like that. Okay? Now notice, if you're negative, the arrows are coming towards you. If you're positive, they're going away. All right? So here's problem 2 on your quiz. Here's problem 2. I've got it written out here. Here's what I want you to do. I want you to draw the field lines. Draw a schematic of field lines. Okay. Draw a schematic of field lines. Oh, we still got about 20 minutes, so it'll take about 5 minutes to do this. And you're going to have one charge is going to be plus 6 microcoulombs, and then you're going to have negative 2 microcoulombs, and you're going to have a negative 3 microcoulombs, and you're going to have a negative 1 microcoulombs. Draw the field lines. But I'm going to add a caveat. Each charge must have a minimum of 2 field lines. Okay? So each charge must have a minimum of 2 field lines. All right? So that negative 1 microcoulombs is going to need 2 field lines. And are those field lines going to be coming into the negative 1 or going away from him? In. So how many field lines would you start with for the plus 6, do you think? There you go. Knock yourselves out. Draw your picture. All right, looks like everyone's pretty much done. Now, so that yours might look something like that. I've got 12 coming up. Now, I've got 12 coming off the plus 6, so that I could get the 2 coming into here. So I should have 12 lines. 1, 2, 3, 4, 5, 6, 7, 8, 12. And I do. Now, here's Gauss's law in a nutshell. And I'll go through the other parts of Gauss's law here in a minute. But I'm just going to tell you the big idea of Gauss's law. Then we're going to go into homework problems 10 and 14. Well, 3, too. Some people were having trouble with 3. We'll do 3, 10, and 14 real quick here at the end of class. But here's the idea behind Gauss's law. What if I drew a ring, a big circle, around all these charges, like that? What's the electric field on the outside of this? Exactly. It's 0. Let's get rid of this charge right here. Let's get rid of this charge. Okay. Now,
Can you do that though? Because I mean, then you have 10.
exactly. That's what I was getting ready to, right. Okay. Here's what Jack, wait a minute. It's not 0. So now my question is the electric field on the outside 0 now? No. But you know what we've done? We've created an electric field that is just like this. We just created an electric field just like that. All right? This is what we've done with this. Okay? Some of you look at me like, what?
In that spot or all the way around it?
Let me draw it better. Let's say the electric field depends upon the area, too. And we'll get to all this on Friday. This is just kind of laying the groundwork for Friday. So let's say we had a +3 and a -2 and a -4. Like this. Oh, and let's say let's put a +2 down here. Okay? Now, we're going to draw a ring around this electric field. Okay? That would be the same thing. So the electric field coming out of here at this point right here. Oh, did I draw that correctly? Which way should those arrows be going? Just looking at this. In. Exactly. These arrows should be going in. Okay? Because it's the same configuration. There's no difference between that and this guy. Well, I'd need to. There. Now I've got 6 up coming in, so makes it the same. That's Gauss's law. You can look at the whole picture and go, oh, I want to get all this charge inside this certain area, okay? And then I'll have a net charge that'll have an electric field on the outside of it. Same thing. And it's a pretty ingenious little thing, but we didn't get to the other, the ideas in that lead up to that. But let's go ahead, and we will cover that on Friday. Let's go ahead and do homework problem 3. And I think we can just do 3 and like 14, and you should be able to get, because 10 is just like 14, I think. Wasn't it? Pretty close? Not at all? It wasn't even close. Oh, okay, maybe we should look at 14 too. No, that was 19. That was 19. All right. Take a look at this real quick. All right. I got some folks who are having trouble with problem 3. Now, here's what I've got for problem 3. It says I have a metal sphere has a charge of 8 microcoulombs. What is the net charge after 6.0 times 10 to the 13 electrons have been removed? And I forgot to bring my calculator, so I won't be able to get an actual number. But here's the deal. Let's say we've got Q. We know this. We know that Q, the total charge, depends on the number of electrons or protons times that unit charge, that very basic unit charge in the entire universe. We haven't found any, we can't get any charge any smaller than that, of 1.6 times 10 to the negative 19 coulombs. We know this. All right, we know that my original charge, my Q naught, is 8.0 times 10 to the negative 6 coulombs. Okay? Now then, if I remove I'm going to place, okay, so it's a positive charge. Now, if I put a bunch of electrons on there, if you think to the electric field, I'm going to put a bunch of electrons on there, okay, is that charge going to increase positive, or is it going to go down? It's going to go down because electrons have what kind of charge? Negative charge. And they gave me the number of electrons is equal to 6.0 times 10 to the 13 electrons that I put on there. So the charge of the, so basically what I have to do is I have to add the two charges. So the charge of the electrons is going to equal 6.0 times 10 to the 13th times negative 1.6 times 10 to the negative 19 coulombs. Okay? And notice that's going to be a nice little negative number. And so my net charge, my Q net, is going to equal Q naught plus QE. That's the way you do that one. And that should lower. Some of you might have had a negative thing and they're adding protons. If you had that, it's the same thing. You just reverse the signs is all. Okay? Y'all see that? Was it asking for the number of electrons?
I don't know, I don't remember
The net charge after.
What is the net charge? Yeah, Q net. It's asking for the net charge. Number 2 is asking for the number of electrons. How many electrons must be transferred? Okay. All right. What else do we have? 10? Let's look at problem 10. Or is 14? Oh, 14 looks more fun. Let's try 14, because I think if we do 14, you can do.
Wait, which one is the one with 3 points? Can you do that one?
Yes, that's 10.
Yeah, do that.
All right. That'll work. Okay. Here's the problem. The problem says a charge Q is located at the origin. So let's just draw a thing here. Got a plus Q here, sitting there at the origin. All right. And then while an identical charge is located on the x-axis at 0.5 meters away, there's an identical charge, plus Q, right here. All right? And he's 0.5 meters away. All right? Now then, the third charge of positive 2 cubed is located on the x-axis at such a place that the net electrostatic force on the charge at the origin doubles. Okay? Its direction remaining unchanged. Where should this charge be located? Okay? So we're going to put a plus 2q on there somewhere. Right now, let's call this charge A, B, and then we're going to put a force on there of C, and we got to figure out how far away we're going to put that and where we're going to put that. Right now, let's take a look, before we put C on there, let's take a look at the force of A on B. The force on A caused by B. Which direction is that going? To the left or to the right? Which way? Which direction is the force? Okay. The force on A caused by B is going which way? Right or left? Why is it to the left? They repel. They're like charges. So the force on A caused by B is going this way. They don't want the direction of it to change. What would happen if I put a positive charge over here? What would happen to that force? It would change. It would go, oh, I'm going to go this way. So if we want to double this force, where should we charge the 2q? Yeah, we're going to put it over here on the right somewhere. Okay? We're going to put it on the right somewhere. Okay? So let's go ahead and figure that out. Where do we put 2q? Double the force of AB. First of all, let's figure out what the force on AB is. Force on AB is equal to K times Q squared over 0.5 squared. Correct? Is that a correct answer? Okay. Now what we've got to do is we've got to double this guy. And I'm going to put a 2q force on there. All right. So that we're going to put a 2q force on here somewhere, so that we get this. So we're going to get the force of A on C is equal to the force of A on B. Because if I do that, then I take the sum of the two forces and I get double the force, right? Because what we're after is the sum of the forces on A is equal to force of AB plus the force of A on C caused by C. All right? And the goal was to get this equal to 2 times FAB. So therefore, FAB has to equal that one. That was probably the hard part in that one. There might be an easier way to do it, but that was my inspiration I just now had. Now, let's think about the force of A on C, caused by C. We'd have K times Q times 2Q over some R squared equals K times Q over 0.5 squared. Ooh, I like this. This is nice. Why? Yeah, we're going to have a canceling party, okay? We get rid of K. We can get rid of Q. And the only thing we're left with is 2 over R squared. So this will solve out to be 2 over R squared equals 1 over 0.5 squared. So we wind up with 2 times 0.5 squared equals R squared. Take the square root of both sides. We wind up with square root of 2 times 0.5 equals R. And I think everybody's 10 was the same. No? What did yours say?
I mean, I just said different, numbers.
It did?
Yeah.
Did it have different charges?
No.
Hopefully it's still Q and 2Q.
Yeah. It's all
Oh, just the distance was changed? Okay. All right. So there. Yeah, that one was tricky. I had no idea. I thought I was just going to ask you. Sorry about that one. All right. Was 14 about the same thing? 14. They're separated by a distance of 2.5 centimeters. Oh, 2.5 centimeters. Be careful with Wiley plus. What must you do? Convert to meters. Okay? 2.5 centimeters. What is the magnitude of the force that each sphere experiences? And what is the force attractive or repulsive? Okay? The spheres are brought into contact and then separated. Ooh, that's kind of fun. They're brought into contact and then separated. What's going to happen? All those negatives are going to go join their positive brethren. Okay? And then it'll wind up with a positive charge at the end. So that one's not too bad. That one's not too bad. That one's 10 was the tricky one. All right. Okay. I know you all have lab here, but one advantageous office hours that we can have. Now I've got a meeting at 2 o'clock, so I'll have to leave at about 10 till. But I'll be in my office from a quarter after until 10 till. So during that time when you're killing time between lab, if you want to come ask questions, like if you're still stuck on 14 or something, you can come and we'll do it. Okay? All right. So you've been good. I will not, for my video recorders, probably use the slides ever again. Okay? I hate that. I hate it because I was sitting there going, God, he doesn't even know how to use the gyro mouse. You're right, I don't. I know how to use chalk or Blackboard. Okay, so that's what we'll do. We'll do Gauss's law, and we'll probably start 19. Oh, don't forget to turn in your quiz. Yes, Mr. Random. I forgot to collect your. So I'll collect your quizzes. Everyone should already have a nice positive 10 points. Yay, team. I'll go in and change your homework scores for you all. We'll get that fixed, so you'll be fine. All right.